Good morning, ladies and gentlemen. So, semester break is over, and we coming back to our course, Advanced Quantum Mechanics. And we'll start with a session, supervised session on homework. Homework is due to March 2nd, if I'm not mistaken. So we will talk about homework today. Let me remind how do we proceed. It is we have had already a supervised session. So first of all, I will go once again through formulation of the problem. So there will be two problems. I will do them separately. Then, if you have questions, and I assume you have, just put these questions to the chart. Instructors will follow the chart, and they will. No, sorry, I put it wrongly. If you have a question, please raise your hand, and an instructor will contact you in a chat, individual chat. Then you have an opportunity to formulate a question, to get a response. And if the question is interesting for everybody, then an instructor would speak up and explain the question to everybody. All right, do we remember anything? Did I forget anything? Right, just why don't you react in the chat? Because yeah, I still miss interaction with all of you. I hope I'm not muted. Clear, it's clear for everybody. Good, so let me open the first problem. Let me go through this. Fine, so homework number 4. I need to adjust the window. Very good. So we start with electrons in a metal in the presence of phonons. Electrons are fermions. Phonons are bosons. They are excitations, basically oscillations of crystal lattice of this metal. Let us look at the Hamiltonians. So it contains as many Hamiltonians we consider 3 terms. This is to describe electrons. This is to describe phonons. And there is interaction between these two. Fine, so what do we have for electrons? For the phonons, we have a standard spectrum of non-interacting particles. At the moment, we do not specify dependence of electron energies on the wave vector k. Neither we do this for phonons. Energy is just some functions of corresponding wave vectors. To kind of sort out things to introduce good notations. We will try to call wave vector of the phonon by Q and the wave vectors of electrons by K. All right, so it's all clear for us with electrons and phonons terms. Those are simple terms of non-interacting particles. Interesting aspect is interaction, and look how does it look like. Right. First, there's some interaction constant, and it depends on two energies of electrons involved. Right. What are electrons involved? To understand this, let us consider one of these terms. These terms are just complex conjugated to each other, so it would be sufficient to consider only one term. So again, it is one of the crucial questions which always will pop up in the course of examination. You have to understand what each term in perturbation Hamiltonian does. Right? So what does this term do? It creates a phonon in a certain state, Q, and it does something with electrons. What does it do? It annihilates an electron in the state K and creates it to the state K minus Q. We choose it like this because of conservation of momentum. So the sum of K vectors is zero, basically. Alternatively, one can say there was an electron in the state K and it has been transferred to the state K minus Q with emission of a phonon. Again, I repeat again and again that it is basically, well, I do it before actually going to concrete points as a problem. But I want to just emphasize already now that this is crucial. One has to understand how elements of perturbation Hamiltonian work on the state. So what do they do? Fine. All right. So we skip electron spin for brevity. One could also consider different spins of electrons, but it doesn't matter much in this context. Right. As promised, we deal with this interaction by means of perturbation theory. Right. If we disregard interaction completely, that's what this equation means. No interaction at all. The system is in a ground state, and some ground state which is familiar for us. Let us see. First of all, there are no phonons. It's ground state with respect to phonons. No phonons are always excitations. They cause positive energy. And right, this is the ground state is vacuum with respect to phonons. As to electrons, we have this expression. What do they, again, what does it mean? It means that we have created electrons in all states within a hemisphere, with radius kf. which comes to all state, which is equivalent to all states below certain energy, Fermi energy. All right, this is a ground state, and we will compute correction, energy correction to this ground state, owing to interaction with phonons. Good. Then at this point we didn't specify what are these functions, and now we come with gross simplifications because again, for all these problems, we always try to make algebraic part, calculation part, as simple as possible. Right. So we assume that all phonons have a same frequency. This is called Einstein approximation, actually, and of very many things Einstein did for us. That was the most stupid one. Who can perhaps explain me why? A kind of hint is to recall what we talk about phonons in the lecture, what was that, number 6, a little bit in number 7, when we consider quantizations of phonons in an elastic string. Why this approximation is rather stupid. Although, of course, it's very convenient from illustrational point of view. Hmm? Is that nobody knows, or you just kind of yet
Don't know.
sleeping? Please put something to the chat. If you don't know, put chat that we don't know. Fine. Let me recall some important thing which we understood when we talk about phonons, about deformation of lattices. If one considers this frequency of a photon depending on Q, in the limit of low frequencies, in the limit of small k vectors, so that in the limit of large wavelengths, the frequency actually goes to 0, because phonons, in fact, describe sound at low energies, at low frequencies, so that for sound, dispersion law is the same as for light. Frequency is proportional to the wave vector. So it goes to 0 when wave vector goes to 0. This is very fundamental. It concerns to all deformations of the lattice. If you just shift the lattice, you don't pay any energy. Right, and that's what Einstein at some stage missed in his model. Well, such things happen even with very clever people. Anyway, we assume Einstein model, all phonons have the same frequency. Good. In addition, we are interested in electrons which are close to Fermi surface. And close to Fermi surface, we can approximate this energy by the following form. The difference of energy from Fermi energy, of course, it should disappear if K equals to Kf, right? So this difference is velocity, a constant, times delta K. And what is delta K? It's just a difference between actual wave vector and the Fermi wave vector. So it is zero at Fermi surface. It is positive beyond Fermi surface. It is negative within Fermi surface. Right. We assume that these energies are such that this delta K is smaller than Kf. This is, by the way, guaranteed by this condition. The frequencies of the phonons are supposed to be much smaller than Fermi energy. By chance, it's also the case of all metals. Phonon energies are kind of a couple of orders of magnitude are lower than corresponding Fermi energy. Good. Then we define a letter, convenient letter, which we use further on. It is a density of states near the Fermi surface. Let us see how we define it. All right, so this epsilon is energy difference from Fermi surface. And to define density of states in general, well, we just count how many states are there in energy interval in an interval in energy space. That's why we put this delta function that cuts a tiny interval in energy space and we integrate it overall K. So this is the density of states. We will see these formulas, similar formulas, several times in our course. Right, and again, we assume that it doesn't depend on epsilon, again, near Fermi surface, and we are near Fermi surface because of this approximation. Good. Now, finally, we got to the business. Now we have concrete states, concrete things to do. Right. First point A is just warming up. We don't do any advanced quantum mechanics. We do something which you have learned in solid state physics. Right, or did in the course of solid state physics. I hope we just compute the above integral. You could do it just purely mathematically, or you can recall what you have heard in solid state physics. Anyway, it is a computation of this integral. Good. So we have an expression for this nu in terms of parameters, in terms of Kf, and in terms of Fermi velocity, velocity at Fermi level. So basically, we implement this formula. All right. So this is warming up. Point A. Anybody has questions about formulation of this point? Not about how to do this, that you will ask later, but just about formulation, no problems. Good. Then again, point B. Point B again, let me repeat it again and again, because many students still have a difficulty with that. It's a very crucial point in any problem which you got. Most problems in homework, most problems during the examination. You have to understand what do the terms of this interaction Hamiltonian. Not the whole guy, but the terms. What do they do with the ground state? Which states come about upon the action of this term on the ground state? Right. We have two terms in interaction, and let me say it again. It's not a kind of big mystery that if this term acts on this ground state, it doesn't do anything because, there are no phonons to annihilate. So we can concentrate only on this term, only on these terms. Fine. So we get a series of states that we need for further calculations. They all have one phonon and are labeled with two-wave vectors. Right, sir. It's not kind of rocket science, but you are still invited to write down this state explicitly in terms of creation and annihilation apparatus of electrons and phonons, and give the restrictions on moduli of these two K of these vectors. Good. Again, I don't explain how to do this. I just explain the formulation. Any questions about formulation? Again, I would stress that this question, this point would be present in all questions. Okay, what do K and K prime represent? As it said, those are two wave vectors of the electrons involved. Right? What does it mean? What does it imply? It means that if you look at this term, you will understand what are electrons involved. Okay? Let me put it in this form at this moment. Other hints you would get when you ask the questions. Electrons involved. You look at this term, you'll figure it out. Let us see them. It is already some work. Let's have an excited state. This is a state. It's an alternative to the ground state we have looked at. It's simplest alternative one extra electron with wave vector k1 and energy that was put into has been created. Right. Then this mere electron, not all electrons present, but this mere electron loses energy emitting a phonon. The possible final states are labeled somehow, and you invited to write down these states again as you did in point B. Okay, so again, points B's and C's, they're simple, they don't require any calculation. One just has to understand how creation and annihilation operators work, but one has to understand it ideally. Fine. Now, finally, there's some work to do, and this is correction to the energy of the ground state. That has been already assumed, and okay, we repeat itself. It is a bit of repetition. We just got energy dependence of density of states, and we compute this energy, right? This is general formula. So A and B here just label all possible states in Fock space. But you understand immediately that you don't need all this Fock space of this multitude of all states in Fock space. Well, you just need to concentrate on the states you have already computed, right? Why is it so? Because interaction Hamiltonian between ground state, which acts on the ground state, will have matrix elements only to these states. Fine. So points B and C are just to prepare you to do actual calculation, which you do. Right. And then you're invited to show that correction assumes this form. It's proportional to the volume, but yeah, it's also natural, kind of its energy of the whole system proportional to volume. And one needs to reduce the equation to this form and say what X actually is. All right, so there are some calculation which involves calculation of matrix elements and summing them up and somehow transforming it to the form of integral over energy. This is point D. Let me also talk about bonus point because it's also kind of interesting, logical, and yeah, I could not make it compulsory at this moment, but I think it's a serious and interesting question. Namely, we talk about addition energy. We have computed the correction to the ground state energy. We also have this extra excited state. So let us talk about the energy difference, correction to the energy difference between this state with one phonon, with one extra electron, and the ground state. And one needs to compute the second order correction to this addition energy, not to the whole energy of the system, but to the energy of individual electron with a wave vector. Let's see, what was the wave vector? K1. Uh, right. It's some hint how to do this. And it's eventually very practical task because in this case you compute correction to the spectrum of excitations, not to the whole energy, which is difficult to measure. You compute correction to the spectrum, which is can be observed by, well, exciting the electrons in this metal. Very good. So I believe I explained the formulation. Any questions about formulation? If not, we just perhaps I will close this window. We don't need it. You have this formulation in your hands. I close this window, and again, if you have a question, please raise your hand, and an instructor will attend you. Right? It is good if the instructor writes into the chat that I will take this certain question, certain student, and also when instructor contacts you, please lower your hand. Agreed? Okay, let's make it a go. I guess it, okay. Paul, I will take care of you. All right. Time is going on. I guess I need to explain second problem at the moment. So problem number 5. Let me find it. All right. It's about magnetic impurity. Mm-hmm. That's actually my favorite problem. Um, Good. So what do we have? What is the situation we are in? We still are in a metal with electrons. And we put a single, how to say, potentially magnetic impurity in this metal. So there is infinitely many states in the metal which are filled. Some of them are filled, some of them empty, and there is a single impurity, which is just one level. One can put a different number of electrons on this level. It is spin split, so there can be no electrons at all. It can be single electron or two. All right, so this the whole structure Hamiltonian is, I would say, generic. We have terms describing one system, impurity, terms describing electrons, and some, I would say, interaction. But yeah, in fact, it's not interaction; it's a mixing of the states in this case. Yeah, and we will treat this mixing by perturbation. Good. Let's perhaps start with something which we know. Those are electrons. Those are electrons, and spin is important in this problem. That's why I put this spin explicitly. Good. Non-interacting electrons. In addition, I want to specify, sorry, not in addition. Now I want to specify the energies for impurity. And look, I put it like this. What are n's? N's are just numbers of electrons with a certain spin. Formally, they are defined as a combination of creation and relation operator. But if you just look at the impurity, you don't need it. You don't need it absolutely. Right, those are just numbers. So one can have no electrons, and then the corresponding energy is 0. With 1 electron, it is epsilon. Could be 2 spins, it's epsilon. And for 2 electrons, yeah, it's just this. No, sorry, I put it wrong way. For 1 electron, it is epsilon plus u in this form, or in these notations. Fine. So this are Hamiltonians for impurity and for metal. You see there is some interaction at the impurity. U shows how intensive the interaction is. Good. And then we have this perturbation term. We have the mixing between the localized level and the electron levels in the metal. So what is this mixing? It means that electrons can go off impurity to some state in the metal. And vice versa, it can come from the metal and sit at the impurity. How we write it down? Look, this is for spin up. It annihilates an electron at the impurity and it creates it in the metal. So we have transferred an electron from impurity to the metal. Okay, this does the same with opposite spin and conjugated operators. Yeah, they do conjugated things. They annihilate electrons in the metal and create it as impurity. Good, that's what the terms do. Again, once again, I need to stress the importance of understanding what do the individual terms do. Fine, and in addition, we have a coefficient which characterizes the strength of interaction, and it's kind of in a rather ugly form. But again, as all ugly square roots which you have seen, they are ugly for a good purpose. It is to simplify the final expressions. So let's accept it that we have here square root of volume, and there's also energy at the Fermi level, which we have recently seen in another problem about the matter. All right, this is the formula for density of states, but in fact it is equivalent to the formula which we have had recently in the previous problem. Okay, good. So we understand the main formulation. Let us understand what we can do about this. Again, so we first neglect the mixing. Point A is always simple. It's hardly advanced quantum mechanics. We look at the impurity because we know everything about non-interacting Fermi gas. It's not interesting. Impurity is simple but relatively interesting. So we figure out how many electron states are there at the impurity. We write down the states and give the energies. Give the energies. We need to use this formula. Fine. Now point B is also relatively simple but important. We compare these energies and we will figure out the ground state of the impurity with no mixing. At different values of all these things. So there are 3 or 4 possibilities, 3 equivalent possibilities, and one has to compare those and figure out them. The ground state of the impurity corresponds to a single electron. If there is a single electron, then the impurity is magnetic, right? It has spin which can look into different directions, so there is a simple realization of a magnet. Right. Then we we do a real calculation which has to be done. It's relatively simple calculation. We need to compute the correction to impurity charge in the first order, in first non-vanishing order in the perturbation, and that will be second order. Correction to the impurity charge proportional to gamma. We need to find corrections to the probabilities to find the impurity in some other states. I believe there is a formula for this, right? So probability to find the system in the state B as a result of perturbation H int, if it is in the state A in the absence of perturbation, is like this. One can one can see that it corresponds to usual perturbation theory. It is a correction to eigenvector to the state A because of perturbation, right? Square root of this correction will give you probability to be in this state. Okay, right. So for this, you need to sum up over all states and to compute the correction to the charge. Good. Next, so this is really calculation part, which everybody has to do. Then there is a less sensible part, I would say. Less sensible in the framework of this problem. We are given a wave function, which can be used as a probe wave function, in fact. So it has adjustable parameters. And right, there is a very simple technical work to be done at this point. One has to explain something. Looking at how these operators work on the ground state. And write down normalization conditions. So basically normalize this function, compute its norm. Right. As to the bonus point, one needs to utilize this function as a probe function. So, as we did, for instance, for a magnet, for big magnet, not a single magnetic impurity, we just compute energy corresponding to this function and minimize it with respect to all A's. That will make it. Good. That is a formula which one needs to employ for density of states. It's about sorry. This is a formula which shows you how to utilize density of states in the context of the problem. So summation of any function which depends on energy can be reduced to the integral of this function over energy. And density of states pops up over here. Fine, sir. I believe that I explained formulation. So let's go and ask questions. Please raise your hands and we will take care of your questions. I should stop window perhaps.